We've sent probes to every corner of our solar system, to the Sun, to Jupiter, even beyond the orbit of Neptune, but two destinations remain almost impossible: Pluto and Proxima Centauri. Pluto, a frozen world at the edge of sunlight, and Proxima, a star so distant that even light takes years to arrive. The problem isn't just distance, it's physics itself. Because to reach them, you need to travel faster than anything humanity has ever built, and then somehow stop. That's why, even after decades of progress, both worlds remain out of reach, symbols of how vast the universe truly is and how small we still are within it. For decades, Pluto was the unreachable dream, the cold, silent frontier at the edge of the Sun's dominion. More than 6 billion kilometers away, it lies so far that light itself needs hours to make the trip. In the 20th century, just imagining a mission there felt like planning a voyage to eternity. And yet, humanity tried. In the early 1970s, NASA's engineers discovered a rare celestial opportunity. Between 1976 and 1978, the outer planets, Jupiter, Saturn, Uranus, and Neptune, would align in a way that happens only once every 176 years. With precise timing, a single spacecraft could use their gravity to slingshot across the solar system, saving decades of travel time. It was called the Grand Tour, and it was supposed to include Pluto. The mission design was brilliant. 4 spacecraft visiting every major planet in one continuous journey. But the price? Astronomical. When NASA canceled the Grand Tour due to cost, only 2 smaller probes survived, the ones that became Voyager 1 and 2. At first, Pluto was still on the table. NASA even considered sending Voyager 1 there after Saturn, but a last-minute decision changed everything. Scientists chose to redirect it toward Titan, Saturn's largest moon, a world with a thick atmosphere and potential for life. It was a scientifically sound choice, but it meant Pluto was cut out of the mission forever. From that point on, Pluto became the planet that always slipped away. Throughout the 1980s and 1990s, proposals kept resurfacing, smaller, faster probes that could reach Pluto before its fragile atmosphere froze as it drifted farther from the Sun. But every time budgets collapsed, priorities shifted, and time ran out. It was simply too far, too slow, and too costly. Even solar power was useless out there. Sunlight was just a faint whisper. Any mission to Pluto needed radioisotope generators, nuclear power, and even then, energy would be limited. But a handful of scientists refused to give up. Among them was Dr. Alan Stern, a planetary scientist who led the charge for decades. He argued that Pluto wasn't just a frozen dot, it was a world, one that could hold secrets about the solar system's origins. His persistence finally paid off in 2001 when NASA approved New Horizons, a small nuclear-powered spacecraft built with a single goal: reach Pluto before it was too late. Launched on January 19, 2006, New Horizons became one of the fastest human-made objects ever created, accelerating to over 49,000 kilometers per hour. Even at that speed, it still took 9.5 years to get there. When it finally arrived on July 14, 2015, it didn't stop. It couldn't. It raced past Pluto in a single flyby, capturing the first and only close-up images of that distant world. For a few days, humanity saw what once seemed impossible: glaciers of nitrogen ice, blue hazes, and a heart-shaped plane carved into the frost. But even in triumph, the truth remained. Getting to Pluto was never the hardest part. Stopping there was. When New Horizons flew past Pluto in 2015, it didn't slow down. It couldn't. And that single fact explains why reaching Pluto and beyond is so deceptively difficult. It's not just about getting there. It's about stopping once you do. In space, speed is survival. To escape Earth's gravity, a probe must accelerate to at least 11 kilometers per second. To reach the outer planets, it needs even more, tens of thousands of kilometers per hour. But the farther it goes, the faster it must move to complete the journey before decades turn into centuries. And every kilometer per second gained on the way out must somehow be undone if the spacecraft ever hopes to slow down. That's the paradox. The faster you travel, the harder it becomes to stop. When New Horizons left Earth, it was designed for one purpose: a flyby. It didn't carry the fuel or propulsion system necessary to break into orbit around Pluto. Doing so would have required a rocket stage almost as massive as the spacecraft itself, plus decades of extra travel time. At 6 billion kilometers from the Sun, sunlight is so weak that solar panels would barely power a light bulb. And chemical fuel, the kind used to reach orbit around nearby planets, becomes useless when you need to decelerate from 49,000 kilometers per hour in near-zero gravity. To enter orbit around Pluto, the probe would have needed an engine capable of firing continuously for months and an enormous supply of propellant. Even a tiny burn at that distance requires staggering energy. Every gram of mass adds years to the mission. So instead of trying to stop, New Horizons simply flew through, capturing as much data as it could in the few hours it had while racing by at incredible speed. And that's the same challenge that makes Proxima Centauri even more impossible. If reaching Pluto took 9 years at record-breaking speeds, imagine traveling to the nearest star, more than 4.24 light-years away, or 40 trillion kilometers. At the velocity of Voyager 1, humanity's fastest interstellar probe, the trip would take 76,000 years. And even if we could somehow accelerate to a fraction of the speed of light, we'd face the same dilemma. How do you stop when you arrive? A spacecraft traveling at 10,000 kilometers per second, just 3% the speed of light, carries kinetic energy equivalent to thousands of nuclear bombs. Slowing that down requires propulsion systems far beyond our current technology. Nuclear engines, ion thrusters, even advanced plasma drives like VASIMR could cut the travel time to Proxima from millennia to centuries, but not enough for a human lifetime. And every improvement in speed multiplies the braking problem. You can't simply turn around in interstellar space and fire your engines. You'd need as much energy to stop as you did to start, and most of that fuel would have to be carried from Earth. In other words, the faster you want to go, the heavier your ship becomes, and the harder it is to move at all. That's why missions like Voyager, Pioneer, and New Horizons never slow down. They're designed to drift forever, carrying humanity's curiosity out into the dark. They can escape the sun's gravity, but not their own momentum. It's humbling to realize that in the grand scale of the cosmos, we've only taken the smallest of steps. We've learned to throw our machines into the void, but not yet how to bring them gently to rest on another star. For now, Pluto marks the edge of what we can reach, and Proxima Centauri remains the edge of what we can only dream about. Humanity's journey to the stars has always been limited by one word: propulsion. Every leap forward in exploration from the Moon to Pluto has been defined by how fast we can accelerate and how efficiently we can slow down. But to reach beyond the solar system, we need to reinvent motion itself. Today, the spacecraft we launch still depend on chemical propulsion, the same basic principle used since the 1960s. Powerful, yes, but incredibly inefficient for deep space. To reach even 1% of the speed of light using chemical fuel, a probe would require a tank with more mass than Earth itself. It's absurd. And that's why scientists began to dream differently. One of those dreams is ion propulsion, engines that expel charged particles at tremendous velocity. They're slow to start, but in the vacuum of space, they can burn for months or even years, gradually building speed. Missions like Dawn have proven their reliability inside the solar system, but even these futuristic thrusters would take tens of thousands of years to reach Proxima Centauri. Then came VASIMR, a plasma engine developed by former astronaut Franklin Chang Diaz. Using magnetic fields to accelerate ionized gas, it promises journeys to Mars in just over a month. In theory, it could cut interplanetary travel times by a factor of 10, but even if perfected, a VASIMR ship to Proxima Centauri would still need over 2,000 years to get there. That's when engineers turn to the stars themselves for help, to the light that shines from them. Solar sails work not by burning fuel, but by catching photons. Each tiny impact from sunlight pushes the sail forward, slowly but steadily. Enormous, ultralight, and fragile, they're like cosmic parachutes drifting on beams of light. They could, in theory, reach another star in 1 or 2 millennia. Still far too long for human ambition, but revolutionary nonetheless. And then came a radical twist on the idea: laser sails. Instead of waiting for the sun, we could use Earth-based laser arrays to push the sail at unimaginable speeds. This concept became Breakthrough Starshot, a plan to send swarms of microprobes, each the size of a coin, to Alpha Centauri at 20% of the speed of light. The journey, only 20 to 30 years. It's bold, dangerous, and maybe the first step toward interstellar travel within our lifetime. But there's a catch. Even at those incredible speeds, the probes wouldn't stop. They'd flash past Proxima in seconds, capturing everything they can before being lost to eternity. The truth remains: we've mastered the art of leaving home, but not yet the science of arriving somewhere else. For centuries, humanity has stared at the night sky and seen distance as a challenge, something to be conquered. From the first telescopes of Galileo to the robotic eyes that now wander through the darkness, our species has always asked the same question: how far can we go? But now, standing at the edge of what we've achieved, the answer is humbling. We can go far, but not far enough. Pluto and Proxima Centauri stand as 2 cosmic mirrors, one at the frozen edge of our sun's light, the other orbiting a distant star. And between them lies the same barrier, the cruel mathematics of distance and energy. We reach Pluto with brilliance and stubbornness. New Horizons showed us a world of mountains made of ice and plains shaped like a heart, a symbol of endurance frozen in nitrogen and methane. But even as those breathtaking images arrived, the probe was already racing away, silent and unstoppable, never to return. It was a victory that came with a price, proof that visiting the edge of our solar system is still closer to a miracle than a routine. And Proxima Centauri, it mocks us from just beyond reach, a mere 4.24 light-years, our closest neighbor, and yet impossibly far. At our fastest speed, a probe would take longer to get there than all of human history itself. Even if we could build ships capable of crossing that gulf, we'd still face the same problem that haunted New Horizons: speed without control, motion without return. Every proposed solution, fusion drives, nuclear pulses, antimatter engines, solar sails, faces the same cosmic truth: space is vast beyond comprehension. Each meter per second gained requires energy on a scale that defies practicality. And even if we solved propulsion, communication would break down, navigation would falter, and the time delay between now and then would turn into decades. The deeper you go, the more alone you become. That's why missions like Breakthrough Starshot matter so much. Tiny ships, lighter than a sheet of paper, accelerated by laser light. A fleet of 1,000 eyes sent into the void. They might not slow down, they might not survive the journey, but they represent something more important than success. They represent intention, the human need to push forward even when the destination is unreachable, because that's what exploration has always been, an act of faith. When we sent Voyager, we knew it would never come back. When we launched New Horizons, we knew it would never stop. And if we ever send a mission to Proxima, we'll know it won't return to tell us what it found. But that has never stopped us. Each of these journeys isn't just about science, it's about who we are. To venture outward, to reach for what's impossible, is to defy the boundaries written into our biology. We are creatures of gravity, bound to one small world, yet our minds refuse to stay here. We build machines to become our extensions, to see, to touch, to wander where we cannot go. And someday, maybe centuries from now, one of those machines will slow down. It will enter orbit around another star, and it will send back an image, not of home, but of another home. A pale blue dot circling a faint red sun where the story of humanity begins again. Until then, Pluto reminds us how far we've come, and Proxima reminds us how far we still have to go. Between them lies the truth of our age. We are explorers trapped in the slowest century of discovery, standing at the dawn of a cosmic era we can almost touch. So we keep pushing. Each launch, each failed mission, each grain of data from a dying probe, it all carries the same message into the stars. We are here, we are trying, and even if we can't yet cross the interstellar gulf, every light we chase brings us one step closer to who we're meant to become. Because in the end, the road to Pluto showed us that far is only a word. And the road to Proxima will decide whether impossible is one too. There's something haunting about the way our greatest missions end. Voyager, still whispering from the darkness after almost half a century. New Horizons, drifting beyond Pluto, chasing sunlight it will never feel again. And one day, perhaps, the sails of Starshot will do the same. Tiny messengers of humanity, gliding silently between the stars. Each of these probes is more than metal. They're echoes of who we are, dreamers, engineers, explorers. Every signal they send is a heartbeat from Earth, a reminder that curiosity is our oldest instinct. Because the farther we travel, the more we realize space is not just a destination, it's a mirror that shows us what we're capable of becoming. When New Horizons revealed Pluto's frozen heart, it wasn't just science, it was symbolism. At the edge of the solar system, a heart still beats. And beyond that, Proxima Centauri waits, our nearest neighbor and our greatest temptation, 4 light years away. A distance that defines what impossible truly means. Yet we keep trying. We design faster engines, lighter sails, bolder missions, not because we expect success soon, but because hope itself demands motion. And maybe that's the secret of our species. We're fragile, but relentless, limited, but unafraid of infinity. Someday, our descendants will look back and see these early attempts, Voyager, Pioneer, New Horizons, as the first flickers of a cosmic dawn. They'll say, that's when humanity began to expand its horizon, because exploration was never about leaving home. It's about redefining it. So we keep going, past the frozen plains of Pluto, past the fading light of our sun, and into the unknown between stars, not because it's easy, not even because it's logical, but because wonder demands it. And in that pursuit, In that endless reaching, we discover the one thing rarer than any planet or star: ourselves. If you could choose just one destination, would you rather visit Pluto's frozen heart or Proxima Centauri's unknown world first? Tell me your choice and your reason in the comments below. Like this video if it made you wonder how far we'll truly go. Subscribe to Stellar Path and join me as we travel beyond the edge of the known universe.